11.5, the area problem on page 180 in your note guide. This is the last lesson of our unit. Yay! All right, so we are going to investigate how to model application problems involving area under a curve, which is connected to calculus. So, starting off with just a simple problem, we know that rate is equal to distance divided by time. So again, the triangles mean change in distance over change in time. And so it says if it takes you 2 minutes to travel 1 mile from your house, how fast were you traveling? So we went 1 mile, oops, that's an M, and it took you 2 minutes. And so usually we travel in miles per hour. So we'll change those minutes to hours. So in 60 minutes, there is 1 hour. Then we can cancel. So minutes will cancel with minutes. That gives me miles per hour. And so 60 divided by 2 is 30 miles per hour. Now let's make the connection to area. So we are going to go ahead and graph that story problem. We're going 30 miles per hour is the average velocity. And if we look at this graph, we'll have this be our time. And over here will be our rate. And so if she goes for 2 minutes, and again, this would be 2 out of 60. Here would be 1 out of 60. So if she travels 2 minutes and she went an average of 30 miles per hour, here's up to 30. And this area is going to represent her 30 miles per hour. All right, so looking at the average velocity, we know that if I were to look at the area of this rectangle, we know area is equal to length times width. And so this story problem, the area would equal the length, which is 2 out of 60, which is the same thing as 1 out of 30, times, and then the height of that is 30. And so this equals how far she traveled, which was 1 mile. So when we look at this, the area represents the total distance traveled, 1 mile. Now we're going to look at the graph of the instantaneous velocity. So let's say she was not going a constant rate of 30 miles per hour. Let's say that she was at stop, and then at 1 minute, she's here at 30 miles per hour. And at 2 minutes, she's accelerated up to 60 miles per hour. So looking at this, we're still going to have the x-axis be our time, and the y-axis is our rate. And you can see her time, she still went for 2 out of 60 for 2 minutes. And this time she traveled up to 60 miles per hour. So now I'm going to find the area of this triangle under the curve. So we know that this is a right triangle, and the area for a right triangle is 1/2 base times height. And so the area of this is going to be 1/2. The base is 1/30, 2/60 reduced. And the height is going to be 60. And when I multiply this out, I still get 1 mile. So she traveled 1 mile. Now we're going to look at approximating area under a curve. So Riemann sum is the sum of the areas of rectangles that we make underneath a curve. There's 2 types of rectangles we can make. Left rectangles, so the left side of the rectangle will hit the curve, or the right side of the triangle will hit the curve. In example 3, we're going to use Riemann sums to approximate the area of the region bounded by the graph of f of x equals x squared plus 2. So if you didn't have the graph, the first thing you would do is you would graph this function. So you can see this function is graphed right here. Then we are going to do subintervals making rectangles. So they'll always tell you the interval. So we're going to go from 0 to 2. So the first thing you're going to want to do is figure out how wide are these intervals? What is the scale from 0 to 2? And so you'll take the interval that you're looking at, subtract it, and divide by how many subintervals you want. We want 4 rectangles. So this gives me 2/4, which equals 1/2. So what that means is I am going to break this graph up into 4 subintervals. So the left side's going to hit the function, then I'm going to travel 1/2. Left side will hit the function, then I'm going to travel 1/2. Left side will hit the function, then I'm going to travel 1/2, and the left side will hit the function. So we're going to try to find an approximation of the area underneath this curve. Now, we know it's not going to be perfect because when I find the area of those rectangles, I've left out this part here, here, here. So it's actually an underestimate, but regardless, it's still an estimate. The next thing we need to do is then find the area of the rectangles. We know area of rectangles equals length times width. So the width on all these is really easy. The width of all these rectangles is 0.5, and that's what delta x was. So our change in x, we're changing by halves. Now the height of these rectangles, do you see how x is 0 here? So what would f of x be? So basically, if I find f of 0, meaning I plug 0 in to the function, what do I get out? So if you come up here to the function, 0 squared is 0 plus 2 equals 2. So the height of that rectangle is 2. And you can easily see it on the graph. From here to here is 2. So then you're going to just go ahead and find the area of that rectangle. So if you do 0.5 times 2, then you're going to get 1. So the area of that rectangle is 1. All right, let's find the area of the next rectangle. So the next rectangle, this point here is at 0.5. So if I find, for rectangle 2, if I find f of 0.5, which means I'm going to take this function up here and I'm going to plug in 0.5, or 1/2. So what's 1/2 squared plus 2? Well, 1/2 squared is 1/4, and 1/4 plus 2 is 2 1/4. If you wanted to use the decimal, you could, which would be 2.25. So the height of this rectangle is 2.25. So again, now you'll do width times length. So take 2.25 and multiply it by 0.5, and you're going to get 1.125. All right, let's look at the third triangle. So the third triangle, again, we know the width, it's 1/2, but what's the height? We can tell the height just by looking at the graph here. You can see the height is 3. If you wanted to check it, then you would find f of 1. So this is 1. So 1 squared plus 2 is equal to 3. So 3 times 0.5 is 1.5. So this rectangle has an area of 1.5. All right, let's look. And again, here's the formula if you wanted it for number 3. What I'm doing is I'm doing 0.5, and then I'm multiplying it by f of 1, which equals 0.5 times 3, which is going to be equal to 1.5. All All right, let's do the last rectangle. So the last rectangle is 0.5 times f of, and that x value here is 1.5. So we would do f of 1.5. That's going to equal 0.5 times, if you take 1.5, plug it into your original function, you get 1.5 squared plus 2, which is 4.25. And that's going to equal 2.125. So the area of this one is 2.125. So then what we're going to do is, in order to find the area, the approximated area under the curve, you're going to add 1 plus 1.125 plus 1.5 plus 2.125, and we are going to get 5.7. So the area that I just approximated is going to equal 5.750. Now we're going to do the same problem, but this time we're going to make rectangles that hit the right side of the curve. So you can see I hit here on the right, here, here, and here. The width of all those rectangles is 0.5 again, and this time I'm going to show the work up here so you can see the pattern. So if I do width times length, the width of all of these is 0.5. So the first rectangle is 0.5, and then I am going to multiply that by 2.25. And where I got 2.25 is the function is y equals x squared plus 2. If I take here, this is f of this point right here is going to be f of 0.5. F of 0.5. So if I take 0.5 and square it plus 2, I get 2.25. Number 2. Well, let me get that answer. So 0.5 times 2.25 is going to be 1.125. Okay, number 2. We are going to take 1 and we're going to plug that in to the function. So this up here is going to be f of 1. So 1 squared is 1, 1 plus 2 is 3. So 0.5 times 3 is 1.5. Okay, next one. We're going to take 1.5, we're going to plug it into the function. So this is f of 1.5. So you're going to take 1.5, you're going to square it, then add 2 to it, and you get 4.25. So 0.5 times 4.25. And 4.25 times 0.5 is 2.125. And then the fourth rectangle, we're going to take the width again, which is 0.5. We're going to multiply it by the height. The height is going to be f of 2. If you plug 2 in, 2 squared is 4. 4 plus 2 is 6. So 0.5 times 6 is 3. Now I want you to notice I took 0.5 times all those numbers. So in the future, you could take 0.5 and multiply it to 2.25 plus 3 plus 4.25 plus 6. And that's going to be a little bit quicker. The total area is 7.750. And you notice that this number came out larger than the other. This is an over approximation because I'm calculating this area that's above the curve. So let's discuss which approximation is better. I have an under approximation and I have an over approximation. So truly, if I want the best approximation so far, then I can take 5.750 and I can just find the average plus 7.750, and I can add those together and divide by 2. And the best approximation is going to be 6.750. Now this is where calculus comes in, because if I have this curve and I want to find the area underneath this curve, I can make an approximation using Riemann sum. But if I use calculus, this is what we're going to do. We're going to have the limit of those widths of rectangles approach 0. And so I'm going to keep drawing rectangles inside underneath the curve. And what's going to happen is as I take the width of those rectangles and I make that width move to 0, I'm going to draw more and more rectangles under here. And eventually it's going to fill in to where I am actually calculating the area underneath that curve. And so delta x, which is the width of your rectangles, the limit of delta x is going to approach 0. And this is what we call an integral. And an integral, the notation is going to look like this. And if I'm looking at a sub-area between 0 and 2, we'll write 0 and 2. And then we are going to write the area of those rectangles. So I've got x squared plus 2. And I'm going to multiply, that's the length, that's how I found the length of the rectangle. I'm going to multiply that by delta x, which is the width of that rectangle. So this brings us to the definition of an integral. So in calculus, there's going to be two main concepts you're going to work on: finding the derivative and finding the integral. And these are both very key to calculus, and they're super powerful. There's lots of real-world applications with these, looking at velocity, displacement, volume, electrical engineers, all sorts of things. So looking at integral, the value of the area under the curve from one interval a to b is written in this notation. So a is the interval you're starting at, and b is the interval you're ending at. F of x is referring to your function, which is representing the length, and dx is representing the width. And you read it as the integral of f of x dx from a to b. Here's another version of that same thing. The reason why we have a limit is the number of rectangles are going to approach infinity to give us that true area. And this is just referring to the length, and this is referring to the width. So first, the limit has to exist. If the limit exists, then we can say f is integrable on a to b. So on example 4, we'll do it by Riemann sum, and then we'll also use our calculator to find the exact value. Y equals 2 over x, the x-axis, we want to go from 1 to 2 in 5 sub-intervals. So delta x is going to equal, again, delta x is the width of those rectangles, is going to be 2 subtract 1 divided by 5. And so we're going to be doing subdivisions of 1/5 or 0.20. So here, delta x is equal to 0.2. So if you look at these rectangles, the first thing you do is you draw the function y equals 2 over x, and that's a rational function, but we're zooming in on just this part of the function. And we're going to box it in with the x-axis. So we're looking for the area. This one is hitting the left side of the function. So you can see those rectangles are going to hit the left side of the function, where this one hits the right side of the function. So Riemann sum will use length times width. Since the width is 0.2 on the left side, we can do 0.2 times. And then here you're going to find f of 1, and then you'll find f of 1.2, f of 1.4, f of 1.6, and this last one, f of 1.8. All right, so if you find f of 1, you put 1 in for x. 2 over 1 is 2. And then go ahead and try these, plug those in, and let's figure out what the left side is going to be. Now let's do the right side. So the right side, the width, or delta x, is 0.2. And you're going to multiply that by these heights. And again, you're going to find, this time you'll find f of 1.2 plus f of 1.4 plus f of 1.6 plus f of 1.8 plus f of 2. And so I'll stop the video and do that again quickly. Again, how do I find f of 1.2? I take 1.2, I plug it in for x, so 2 divided by 1.2 is what the height of this is going to be. So the right side ended up being 1.291. And you can see the left side is larger because the area over the curve, we're looking at extra area. And the right side is a little bit under, so you can see that number is smaller. So for Riemann's, what we're going to do is you add those two numbers together, divide by 2 to find the average. So we'll just add those two together, divide by 2, and the average is going to be 1.391. However, you can find the exact value by using your calculator and the definition of integral. So here you do green alpha F2, you look for this symbol. You're going to put in 1 and go to 2, and then you'll put 2 over x, and then dx. And if you do that, you are going to get 1.386. And this estimate is so close that we actually consider this the exact value. In this problem, you can use your calculator and plug this in to see what you get when you find the area under the curve. Here's a picture. We're looking for the area from 4 until we get to 12. So we're looking for all of this area under here. And you can see that that's a trapezoid. Because this is a trapezoid, I can just use the trapezoid formula. So the trapezoid formula is 1/2. Then you'll multiply that times the height of the trapezoid, which is 8. Again, if you flip this on it, flip it over, and the length here is 8. And then here's your first base, which is here. And that base is a length of 4. And your second base is over here, and that length is 6. So you can see we got 40 units squared, the same thing that you also got if you did it by the calculator. So now I'd like you to go ahead and try the U-try on your own. Congratulations, this is the last assignment. So good luck next year. You're ready for calculus. Next year in the fall, make sure you come in and say hello. unless we end up back at school, and then I'll see you soon. Thanks. Appreciate you guys. Bye-bye. On the U-Try, I recommend you using your graphing calculator to find the exact value. If you don't have a graphing calculator, then you can set up rectangles in 4 sub-intervals if you would like. And here you go. So this is what the graph looks like, and you're trying to find this blue section. Good luck.